Welcome to Numbers Simplified. In this channel, we seek to simplify and solve numerical problems. Today, we'll be looking at polynomials, specifically the factor and the remainder theorem. Right, before we continue, I just want to help you recall what we mean by the divisor, dividend, quotient, and remainder. For a polynomial that has a divisor, and also having the terms a, b, which are real numbers, ax plus b not being equal to 0. Now, we are going to talk about the factor and the remainder. A factor is a divisor that divides the dividend without leaving a remainder. Take, for example, 27 divided by 3. The quotient is 9 in this case, and the remainder is 0. So, that means that 3 is a factor of 27 because 27 is divisible by 3. On the other hand, if we are going to divide 27 by 4, we are going to get a quotient of 6 and a remainder of 3. Then that implies that 4 is not a factor of 27 because there is a remainder of 3 when divided. Now, with that in mind, I just want you to recall what we did with the synthetic division of polynomials. If you have never heard or not sure of such, please check out our synthetic division of polynomials video, part 1 and 2. Now, we have this scenario, a polynomial, which is the dividend, over the divisor. Now, you would recall from the synthetic division method that we had to equate the x in the divisor to lambda. Then we set the whole divisor to 0. We solve for lambda. In our case, we would have minus b over a. After that, we take that lambda, we substitute it into the polynomial p of lambda. We get r of x, which is the remainder. However, there are two possibilities. One, the first possibility is having the r of x being 0. Then that implies that a of x, or rather ax plus b, is a factor of p of x. Then p of lambda is equal to 0, and that gives us what we call the factor theorem. On the other hand, if r of x is not equal to 0, then ax plus b is not a factor of p of x, implying that p of lambda is not equal to 0, and that is known as the remainder theorem. With that in mind, let's dive into a good example. Example 1. We want to show that x plus 7 is a factor of f of x. So as usual, we set the x in the divisor to be lambda. We set the whole divisor to 0. We solve, we get the value of lambda. In our case, lambda is equal to minus 7. From there, we substitute that lambda into the f of x. Where we have x, we put lambda, or the value of lambda. So our lambda is minus 7, so that we evaluate and get the final answer of 0. So the remainder is 0. Therefore, x plus 7 is a factor of f of x. We can prove it by other means, the synthetic division. So I'm sure by now you know how to use the synthetic division. And from what we have in this synthetic division approach, the remainder is 0. But if you've forgotten how to, or you don't know how to use the synthetic division, check out our synthetic division part 1 and part 2 videos. Those will be helpful. Now, let's get to example 2. With example 2, we have this scenario, p of r, which is the same thing basically. We're just substituting x with r, but the procedure is the same. So the first thing is to make sure that we equate the r to lambda. And from there, we set the whole divisor to 0. We solve for lambda. In this case, our lambda becomes 50. We take that value, we substitute it into the p of r. So where we have r, we substitute it with the 50. That will give us 5 times 50 to the power 2, which is equal to 12,500, which is also not equal to 0, implying that that is the remainder we're looking for. Now, we can check this one out by means of the long division method. Now, you would recall with the long division method, we had to use the divisor and the dividend considering the leading terms. If you've forgotten how to go about the long division, make sure you check out our long division video. That will be helpful. Now, moving on to example 3. Example 3 is a fascinating one because we've got two divisors. Now, how do we go about two divisors? That simply implies that we are going to have two lambdas, lambda 1 and lambda 2. Everything else remains the same. So in this case, we have our lambda 1 from x plus 2, our lambda 2 from x to x minus 1. We set both to 0. We solve for lambda 1 and lambda 2. In our case, lambda 1 was minus 2, and lambda 2 becomes 1 over 2, which is a half. We take these values, we substitute them into the polynomial, or p of x. So for the first one, we set it to minus 38 because we were told that the remainder was minus 38. So we substituted for minus 2 in the p of x. Where we have x, we substitute with the minus 2. We solve up until we get equation 1. We are labeling equation 1 because we are going to reference it, or we are going to make use of it. So it's important that we know what is what, and we label our equations. We do the same thing with the second lambda, lambda 2. We substitute it into the p of x, and we were told that that would give us a remainder of 19 over 2. So we substitute the half. Where we have x, we put the half. We simplify, evaluating, grouping the like terms. We get to the final stage of a plus 2b is equal to 13. That is our equation 2. So we've got two equations and two unknowns. How do we go about it? Yes, your guess is good as mine. We are going to use any other method, but in our case, I think the elimination method seems to be the easier one in this case, where we are saying if we add equation 1 with equation 2, we are going to eliminate the b, minus 2b plus 2b, that's a 0. A plus 4a gives us a 5a. Minus 28 plus 13 is minus 15. We divide throughout by 5. We get a, that is minus 3. Substituting for that a into either equation 1 or equation 2 will give us the same answer. But for the sake of progress, I substitute it into equation 2. So when we do that and evaluate, we get our b being equal to 8. That implies that our p of x is the equation that is given here. That is what we were looking for. We've got our a and our b. Now, let's look at the final example. This one is an interesting example because it makes use of the factor and the remainder theorem. We've got one factor, a divisor that is a factor, and the other one, which is just a factor, or rather, which is just a divisor, not a factor. Now, we have to solve for a and for b. So the first thing we do is to make sure that we get the lambda 1 from 2x minus 1 and the lambda 2 from the x plus 1. But remember, when we get these values, we are going to substitute them into the function p of x. So in our case, we get our lambda 1 to be half and our lambda 2 to be minus 1. We substitute the lambda 1 first because we knew it was a half and because we also know that this is a factor. So that should give us a 0 on the right-hand side. We evaluate, we group the like terms, then we get a over 4 plus b is equal to 21 over 4. that being equation 1. We do the same with lambda 2. Lambda 2 was minus 1. We substitute it into the p of x. We evaluate, grouping the like terms. We get a plus b is equals to 3. Now we've got equation 1 and 2. What would be the easy way out? We can still use the elimination method by subtracting equation 1 from equation 2. Now with that, we see that a minus a over 4 gives us 3 over 4a. 21 over 4 minus, 3 minus 21 over 4, we get minus 9 over 4. A is equal to minus 3. Substituting for a into 2, we get minus 3 plus b equals to 3, b is equal to 6. And then our polynomial is that one there. Right. If you've made it thus far, I would like to congratulate you for a job well done. However, I leave you with the following task. I look forward to hearing your feedback, your comments, and also your suggestions, including your solutions in the comment section. Remember, don't forget to like, share, and subscribe. Thank you so much for watching Numbers Simplified. God loves you.